right, got it? Okay, finishing up 8A today. Talking more about properties of fluids. Okay, first thing. Pressure has been, people have been studying pressure and trying to determine pressure of things for quite some time. The earliest instrument that was built to figure out the pressure was known as a barometer. Have you ever heard of the barometer before?
Yes.
Okay. Where maybe have you heard the term barometer from? Those of you who have heard of the word barometer. Context and maybe where you heard it. Meteorology, okay? You probably heard barometric pressure before. Cloudy with a chance of meatballs, huh? Is that a movie?
Yeah.
You've never seen that?
Who has seen it?
You haven't seen that movie?
I don't watch movies.
Oh,
Kramer.
Oh, that's okay.
Sorry. Okay? So, a guy by the name of I can't say his name. Evangelista. I think he's French. He's a very good evangelist. Yeah, I'm kidding. Torricelli. Okay? He actually was so important that they named a unit of pressure after him. There is a unit of pressure known as the torr. Bet you haven't heard that unit of pressure before. How about the unit millimeters of mercury? Think that would be a unit? Yep. Okay, let me draw a picture of what a barometer looks like. Okay. It's not really the most practical pressure instrument anymore. There's a lot better pressure instruments. Okay, but let me show you what a barometer. Yes. Move out of my way. Exactly. You really can't see that one. I don't want to go that far. That's not smart. Yeah. That's space for that. What's the matter? You look confused. Oh, shoot. Oh, you know what? Yeah, I'm going to wait till they get this in before I describe how this works. Okay. You know why these guys are taking forever. Okay. I'm guessing you're getting close to that. So, you're probably wondering what this is. So what this is just a basin of mercury. So it's some sort of, I want to call it a cup, but you guys know what a basin is? Yes. Okay. Some sort of thing that holds something. So this is mercury, the part that I have kind of slashed. Okay, well the mercury goes up this inverted tube. Okay? And notice how the mercury in the tube is up a certain distance. Okay, we know that mercury actually is fairly dense, so it has some pretty significant weight. So the question you might be asking is, why does the mercury even rise in the tube, or why is it even in the tube? Why doesn't gravity pull it down? Well, the answer is gravity does pull it down, but there's something that forces it to stay up in the tube. Okay? Well, isn't there air molecules all around? Yeah? Okay, and we said that air molecules exert what? A pressure, right? Okay? The more air molecules you have above you, the more pressure it exerts, right? So the weight of the air above it applies a force downward. Okay? Air exerts a pressure downward. Okay? And in order for this to drop, wouldn't the volume here need to raise or rise up? Are you seeing it? Everybody see, if this liquid were to start falling, this liquid would start rising. Does that make sense? Okay? In order for it to rise, wouldn't it have to overcome the pressure that was pushing down on it? Okay? So what happens is when the atmospheric pressure changes, so if the pressure pushing down gets lower, what ends up happening is this starts to fall. Does that make sense? And as this pressure gets stronger, this starts to rise. You understand what I mean when I say that this pressure gets stronger, so it forces it up, and when this pressure gets lower, it allows it to come out. Does that make sense, everybody? Okay, so what they did is they can measure how high this is, and based on a standard that they came up with, they can figure out changes in the atmospheric pressure. What they know, they would say the barometric pressure is falling, okay, when they would see the column of mercury go up. And they would say the barometric pressure is rising when they would see, wait a second. Hold on, I might have said that backwards. Yeah, I said that backwards. That confused some of you. Okay? When the barometric pressure goes up, that means the atmospheric pressure. Right? These particles exerting a pressure downward. If this goes up, will this rise or fall? It will raise, right? You would force it up into the tube. Does that make sense? Okay? So if the barometric pressure rises, you start to see the mercury in the tube rise. As the barometric pressure falls, what happens is as this pressure gets weaker, it allows the weight of the mercury to start pushing it out. Okay, so an increase in barometric pressure allows it to rise in the tube. A decrease in barometric pressure allows it to fall in the tube. And it's really kind of an interesting way that they first discovered barometric pressure, because is this probably the best way to, nowadays to probably study pressure or be able to calculate pressure? There's probably better ways to do it, right? Yeah. They have a lot more electronic devices now that can study the pressure a lot quicker than measuring the height of mercury in a tube. Okay? So, as we continue on, this is where I'm going to spend most of my time. I'm not overly worried about a barometer, but I want to make sure that we do spend enough time talking about buoyancy. Is this a word we've heard? Not much? Yes? No?
Yes.
Okay. What do you think of when you hear the word buoyancy? What? A buoy. What's a buoy? Something that floats? Yeah, a buoy has buoyancy. Buoy!
A buoyant buoy.
Find your way now. There it goes away. ever tried to lift somebody up while in a swimming pool? Is there any significance to that? What do you, does it feel the same? Does it feel different? It's easier. Am I the only one other than Johnny that's experienced this? Have you guys experienced this?
Yes.
If I lift somebody up in a pool, it's a lot easier to lift them up than lifting them up outside of water. The reason why it's easier is because of buoyancy. Okay? And basically what buoyancy is when an object is submerged in water, you have to displace the water. So if I had, do you guys remember the water displacement method? Okay, it was a way to measure the volume of an irregular shaped object, correct? Okay, so let's say I take a really dense object, let's say, you know, big rock, and I put it in here. Probably should make this a little bit bigger. What did we notice happened? The water went up. Okay? So what happened was, as I plop this rock in here, it displaces the water up. In order to do that, in order to displace the water up, it has to overcome the forces of the water to lift the water up. Okay? So, an object will float, okay, if it does not have enough weight to displace the water up. What I mean by that is, if an object is more dense than water, it will sink. And if an object is less dense than water, it will float. So when you jump in water, right, if you didn't swim, you would what? Well, yeah, you would sink, right? Okay? So what does that tell you about your density in relation to water density? You're more dense, okay? As you go down in the water, you displace the water up. Well, that water, due to Newton's third law, exerts a force back on you, doesn't it? Okay? So if you're in the water, okay? You had to displace the water to get in the water. So the water rose. Okay? The amount of water you displaced has a certain force that pushes back on you. So, what happens is it actually ends up reducing your weight because you weigh so much, gravity pulls you down so much, right? Well, the water pushes back up on you based on the amount of water you displaced. So what ends up happening is your weight feels a lot less because of the force pushing back up on you. For example, if I go back to vectors, let's say this is the weight of your body, Fg, right? 200 newtons. Right? Following? Okay? Let's say you jump in the pool and you displace enough water, and the water you displaced had a weight of, let's say 50 newtons. How much do you weigh in water? Any ideas? Take a guess. What? 150. Yeah. Let's say you jump in water. You weigh 200 grams. But you fully submerge yourself. Okay, this is like you submerge yourself halfway. And you fully submerge yourself. So you displace more water, right? If you displace more water, okay, the more water you displace, the more weight you are displacing, or the more force you are displacing. So let's say now you displace more water, and it's 100 newtons. How much do you weigh now? 100 newtons. Have you ever experienced that when you first start to lift someone out of the water, they're a lot easier, but as you begin lifting them more and more out of the water, they become heavier and heavier and heavier and heavier? because what you're doing as you lift them out of the water, that water that you had displaced is no longer displaced anymore. So when you displace water, what ends up happening is you have to apply a force on that water to move. Well, Newton's third law says for every action there is equal and opposite reaction. So the more water you move, the more force it pushes back on you, right? Okay, does that make sense? So if I fully submerge myself, I have displaced more water, so it pushes back more on me, making my weight what? Less. Okay, so as I lifted somebody out of the water, the displaced water becomes less, and it starts to feel heavier and heavier and heavier and heavier. And that's why, like, when you first start to lift them out of water, like, yeah, I feel like I can chuck this person a mile. And then when you get them up to a point, it's like, oh, I can barely throw them now at all. You ever try to throw a little child? No, probably not. You guys aren't parents, so you probably don't know what it's like. But, you know, my son always wants me to throw me out of the water. You know, throw me higher. So, well, you get heavier as I pull you out of the water. Well, not quite as easy. Okay? So, the force, when you displace the water, the force that the water exerts back on you is called the buoyant force. And it's equal to the weight of the fluid displaced. Everybody catch that? The more water you displace, the higher the what? Higher what?
Buoyant.
Buoyant force, or buoyancy, you could say that. Okay? If the buoyant force is greater, then the submerged weight, then if your buoyant force is greater than your submerged weight, you're going to float. For example, if my weight is less than the amount of water I displace, I will float. But if I weigh more than the amount of submerged water I displace, I will what? Sink. What happens if your weight is equal to the weight of the submerged water that you displace? You won't sink or float. What's that mean? If I place you in the middle of a water column, you will just sit there. For example, if I have, a big beaker, okay, and I have an object that has the same density as this liquid, if I place that object right here, it will just look like it's levitating. It'll just sit there. It won't sink or float. But if you put an object in there that floats, what will happen if you put it right here? It will go up, right? Or if I put an object that sinks right here, it will fall down. So if it's less dense, it will rise. If it's more dense, it will fall. If it's equal density, it will what? Stay there. Okay, so let me show you something here. You guys can stand up and come over here. Okay, so this is kind of a dumb question, but which one has the most weight? Which one? I'm talking about these. The one on where?
Right.
Well, this one? This one has the most weight. Okay? So in theory, it's going to be able to displace the most water, correct? Right? Okay? Now the question is, will all of these sink? Will some of them sink? Will most of them float? What do you think? No idea? Alright, check. Well, that let some water in. That one's low. That's cool. I'm gonna take some out. Did I let too much in? If you look, it's kind of cool if you look from the bottom view. You can kind of see all of them are floating, aren't they? They're all floating. So, what is true about all of these guys' density in relationship to the water's density? They're less dense. Okay? Well, we know that a glass container is more dense than liquid water. So if I were to fill this up with water completely, it should sink. Right? But the reason why it won't sink, even though, like, if this was a full chunk of glass, it would what? It'd probably sink. But in its volume, I have a whole bunch of air in here, which is a lot less dense than water. That's why when I put it on, it won't sink. Well, let's go with that. Yeah. So what ended up happening here is, the more water I added, the more water it could displace, because it had more weight. The less water I have, it can't displace the water as much. I wish it would balance a little bit better. The less water it has, the less it can displace. Okay? So, you ever seen the buoys before? You guys know what a buoy is? It's usually when you're swimming, you know, in a lake or something, they'll have a buoy out, right? You're only supposed to go in this zone. Okay? They named them buoys because they apply buoyant force. They're not very buoyant. Okay? Let's see. We have one more slide to do. You know, already see. Okay, it's already good. Already seated. That's cool. I like that. It's to the point where there's enough water on the top that it won't sink. Because the water isn't very, or not the water, there's enough air at the top that it won't sink. Because air isn't very what? Isn't very dense. Okay? Last slide. Oh, I have a lot of rhymes up here. What's the most important thing to think about or know when trying to figure out if something will float or not? Density, how dense it is. Now, can something float in one liquid and then not float in a different kind of liquid? Yeah, it depends on the density of the liquids, correct? Like, a paperclip isn't going to float in the air, is it? It's not going to float. I could take this and put it on there, that floats. And if I take it and put it in a different fluid like the air, it just what? Okay? Because that piece of wood is less dense than the water, but it's more dense than the what? Air. Okay? So it depends on the density of your object that you're trying to see float or sink, and the density of your fluid. So here's just some vocabulary stuff. I'm going to say something's positively buoyant if you have an object that's less dense, and so therefore it will float. It's a positive buoy. An object is negatively buoyant if it does not float or if it sinks. And I think the coolest one is to get an object that has identical densities, and so it will neither sink nor float. Submarines, you guys know that's how submarines work? They make sure that the density of the submarine's equal to the water that it's in, so that it doesn't have to resist changes in density when moving around under the water. When you get this, it's pretty self-explanatory. Just head out.
Yeah, that buoy. That. This is my
If you put an object that's less dense in the bottom, it will float.
towel from my hand.
A little water loss.
What hand to try to wash it? I was going for the heavy thing around here.
Okay.
I think I got it.
Get you an A. It doesn't break.
It doesn't break.
Fortunately, that doesn't always mean it won't on the day.
Okay, good.
Yep. How can I use a sink car flow?
Like, what are the conditions that it would have to be to sink their sink or float?
Like, what would that look
Like, I think I showed this in class. You have some reservoir of a fluid, and say I've got an object that has the same density as the fluid. So if I place that object right here, it won't fall, it won't rise, it'll just sit there. Now, it's not very likely that you're going to find something with the same density as a fluid to get to do this. It's not easy to do that. That's why we don't see this all the time. But if this has the same density, its weight is equal to the weight of the water it just placed. So essentially, when you put it in the fluid, it has no weight. It weighs nothing, so gravity can't even pull it down. Does that make sense?